In this video, let's have a look how we can test for non-stationarity. For that, we're going to use the Dickey-Fuller test. So suppose we have this autoregressive model where we regress the dependent variable y at a certain point in time based on its lagged value, and we have the slope coefficient beta 1. Now recall that under the assumption of non-stationarity, beta 1 would be equal to 1. And that's exactly what we're testing. Under the null hypothesis, we suppose we have a non-stationary time series, meaning that the slope coefficient of beta 1 equals to 1. Under the alternative, we would have the criteria for a stationary time series, namely beta 1 would be less than 1. Now, what happens in software packages though, like Stata for instance, they're doing it slightly different, meaning they take the change in y across time. So they take the difference between, or we call that the first difference. We take the difference between yt and the previous value yt minus 1, meaning we're subtracting yt minus 1 from the right side as well. So on the right side, what we're having is beta 0 plus beta 1 times yt minus 1 plus ut and then minus yt minus 1. This term happens over there as well, minus yt minus 1. Now we call this the first difference. We note it as change in y at a certain point in time t, and over here we have a common factor. Let's take it together. We have yt minus 1, and over here we have yt minus 1 as well, meaning we're going to have yt minus 1. In brackets we're left with the coefficients of beta 1 minus 1. So over here we have beta 1 minus 1, and we're left with the constants of beta 0 and the error term. So beta 0 over here and the error term from there. Now, beta 1 minus 1 is denoted with a new variable in the hypothesis. So let's zoom out to have some more space, and we go over here below. It's the exact same test, but just the notations is slightly different. So under the null hypothesis, the beta 1 minus 1 takes a new variable. For the sake of notation, let's call this gamma. So we're going to say that gamma is either 0 or under the alternative hypothesis, gamma is less than 0. Now why would be gamma 0 under the null hypothesis? Well, recall, under the null beta 1 is 1. 1 minus 1 is 0. So this is just beta 1 minus 1 equals to 1 minus 1 equals to 0. And under the alternative, beta 1 would be less than 1. If it's a smaller number than 1, like 0.8, 0.8 minus 1 is a negative number. So the only option for gamma is to be a smaller value. That's what's happening over here. So we would have that beta 1 minus 1 would be less than 0. So this is a one-sided test. That's the first thing that we need to understand about the Dickey-Fuller test. It's a one-sided test. Because under the alternative hypothesis, beta 1 can only be less than 1 to be stationarity. It cannot be greater than 1. So that's the criteria for stationarity. Now, what happens behind the scenes? What kind of test is this? That's a t-test. So we're taking a t-test where we take the differences between the beta 1, the beta over here. We noted this as gamma already. So we're going to take the differences of gamma in our sample. So gamma that we estimate, and we'll take the differences with the gamma under the null hypothesis, which is 0, divided by the standard error of gamma. That's what's happening. It's a regular t-test. Now, the way to give a conclusion here is to compare the t-score with the t-critical value. And that's the most important part of this Dickey-Fuller test, is that the t-critical values follow a different distribution. They have a specific non-normal distribution, which is already calculated. That's just numbers. I'm not going to go into that. That's something we can Google and see what those t-critical values are. But that's the most important thing. The t-critical values are not from a normal distribution, are not from normal t distribution, not from normal t distribution. So that's the most important thing to understand. And we also have one more thing that matters, is that what kind of test are we doing? Are we doing a test on the regular random walk where we just have an AR1 process without any constant, so without a constant, or in other words, we could call the constant as a drift, right? The other option could be that we have a constant, so with constant, and the last option is that we have a constant and a trend. So over here we would have the constant and plus the trend. All these tests, all these processes have different t-critical values to compare. Different t-critical values. So depending on the test, depending on the model that we're testing, we're going to have different t-critical values to compare with. Different t-critical values. And the value that we're comparing is with the t value that we're finding under our test. So that's the highlight. That's what's happening behind the scenes. It's a t-test. and we're using different critical values from not a normal distribution, and they also differ based on the regression model in that specific case. And one more thing, just for the sake of the practice, let's say that we would reject the hypothesis. What does that mean? If we reject H0, how can we give conclusion over here? Remember, the alternative is that the time series is stationary, but in statistics we can never say anything with certainty, so we're not gonna say that the time series is stationary. We're just gonna say that we have enough evidence that the time series is not a random walk. The time series is not a random walk. We cannot say that we're completely certain that it's stationary, but we have enough evidence to reject that it is a random walk. Anyway, hope this all makes sense, and we are done.